Imagine zooming in on life and getting a clear enough view that you can examine the structure of the Zika virus or see how bacteria attack cells. It's a great honour to speak to one of the scientists behind a breakthrough in microscopy that has achieved just that and been awarded with a Nobel Prize. Dr. Joachim Frank is a professor of biochemistry and molecular physics, biophysics to be precise, and of biological sciences at Columbia University and joins us on the line. Thank you very much for taking the time.
Hi, it's great to be here.
So I understand you got the phone call from the Nobel Committee early in the morning. In fact, you were asleep. Was it one of those stereotypical am I still dreaming moments then?
Yes and no, because it's been widely reported that we also have a dog since 2 months, and it's a puppy, and she keeps us awake a lot. And so we're sort of half expecting that she is waking us up. And just on that morning, the dog, still slept, and we were all woken up by the phone call.
Right.
But it was sort of very unusual. So it was this time it was the Nobel Foundation and not the dog that woke us up.
And I guess the dog doesn't usually wake you up with messages like you've won a Nobel Prize. Were you seeing that coming?
No, and distinctly without Swedish accent.
No.
Yeah.
But did you see it coming at all?
No, well, I sort of had a slight. There was always a slight possibility because especially in the last 5 years, it's been clear that all of a sudden the method took off and like wildfire. So it was conceivable that it could be honored because of its wide impact. But as in every year, there's really no predicting who's going to win the prize. And so I didn't really have my hopes up.
So, well, I mean, congratulations again.
Thank you.
To just zoom in on your research, and quite literally zoom in simple terms, my understanding is that what you achieved was being able to get that very close look at this structure of, for example, the Zika virus by freezing these tiny molecular structures in a way that doesn't distort the view that traditional ways of freezing does, but by freezing substances so fast that you're able to get that, and that's cryo-electron microscopy. Can you explain a little bit further for us?
Yeah, this part of the technology was really developed by Jacques Dubochet, one of my co-winners of the Nobel Prize. So molecules are rapidly frozen in a very thin layer of water, so that they wind up completely immobilized in a thin layer of ice. And in this form, they can be put into the electron microscope without the water sort of getting all over the place. So if you freeze it to very low temperatures. And so you really have molecules inside that layer. Now, the cryo-electron microscopy literally means that you image the molecules in this thin layer of ice. And so originally, people thought this was a very wonderful technique in order to look at molecules that were in crystalline form or in a highly symmetric form. So it was first applied to viruses and thin crystals. And my particular, fixed idea was to try this on single molecules without symmetry. So the Zika virus, in a sense, is not a good example because when you have molecules with a very high degree of symmetry, as the Zika virus, then even a single view gives you so much more information. And you can relate that information to each other very easily. Whereas if you have a totally asymmetric molecule, then it's a lot harder. And so I was convinced that it was going to work, but it was very, very hard struggle to find the right mathematical and computational approaches to do this.
What are the potential applications then for the world in this breakthrough?
Medicine is now molecular medicine, really. It's informed by a very large number of structures, atomic structures, that have been determined by X-ray crystallography. There are more than 100,000 structures in the public database. And together, you get an incredible detailed view of how life actually happens in molecular dimensions. However, many molecules that are of extremely high interest have been left out by X-ray crystallography. And this is because they cannot be put into crystalline form. So there are many molecules, including those that are about membrane structures of channels and receptors and so forth. They're very difficult to crystallize because they need to be in the membrane to be happy. So those structures, as well as structures, very large structures, which are very floppy, and where you want to really see how they change their shape as they perform their work. All these molecules could not be tackled with X-ray crystallography. So I would describe cryo-electron microscopy in terms of closing a huge gap that existed in the knowledge base.
So to better understand these channels as you describe them, does that open up the way to better treatments potentially for some of the toughest diseases to solve out there?
Yes. For instance, I've been involved in work, in a collaborative work with Wayne Hendrickson and Andy Marks, looking at the calcium release channel, and we managed to get the complete structure of the channel in open and closed states and even intermediate states, and we can now infer how the closing mechanism takes place. And the calcium release channel that, for instance, is implicated in heart disease, and for the first time, one can see how one can interact with it, with drugs and so forth, in order to combat certain diseases. So this is one of hundreds or thousands of examples where this method now gives us information that has not been available before.
It does sound very promising. For you personally, as well as the puppy in your life that you described before, you're suddenly now in the public eye. And before we let you go today, I wanted to ask you about your photography, because I understand that you see a parallel, don't you, between your scientific work and your photography that you do on the side?
Yeah, it's really, I think, it's not that one influenced the other, but rather both activities are really results of or the activity of the same mind. Okay, so it's simply, if I go through the world, then I see certain patterns, and some are very interesting. I take pictures of these, and if I go and certain problem, then I have approached it with the same mindset. As I said, at other places, I'm very visually organized, so I really see problems in a visual context.
What's your favorite kind of photography, and do you have any particular ambitions for that side of your life?
No, I'm perfectly happy with the use of photography in which I juxtapose it with texts, and that was something that was made possible by a platform, by a social networking platform called Cowbird. It was created, I think, 2011 or 2012, by Jonathan Harris, and it was at the time it was a very unique site. And then all these other things came up like Instagram and so forth. But this was the first one of this kind, and that was a beautiful way how one can put together images and text and let them play against each other.
Something we're all so used to now, as you suggest, but that's an interesting background.
Yeah.
Dr. Frank, we've got to leave it there. It's always a pleasure to hear from a Nobel winner, 2017 Nobel laureate in chemistry from Columbia University, Dr. Joachim Frank. Thank you for being on our show today.
It was a great pleasure. Thank you. Bye-bye. 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 Bye-bye.